This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Let's now take a look at step-up autotransformers. As previously, it's perhaps easiest to visualize a step-up autotransformer by first imagining a traditional one-to-one transformer with primary and secondary windings having identical turns ratio. Let's say 1,500 turns in the primary and 1,500 turns in the secondary. As previously, let's say this traditional transformer has a 120 volt rated voltage, a 1 amp rated current, and a power rating of 120 volt amperes. Let's again say this transformer weighs 8 pounds. When 120 volts is applied to the primary and given a 1-to-1 turns ratio, 120 volts will appear across the secondary. Via the process of electromagnetic induction, 120 volt amperes of power could be transferred from the primary to the load in the secondary. In the present configuration, no physical electrical connection exists between the primary and secondary, and these windings could be considered to be electrically isolated from one another. If isolation isn't a necessity, consider the following modification. Configured as a step-up autotransformer, one would connect the two windings in a series aiding fashion, and primary input voltage would be applied to one half of the now conjoined single winding. If you want to think of it this way, the primary input winding has 1,500 turns, and the secondary output winding has 1,500 plus 1,500, or 3,000 turns, even though they're part of the same winding. We've in effect created a 1-to-2 step-up autotransformer. Given these two coils are inductively linked, if 120 volts is applied to the primary, 120 plus 120, or 240 volts appears across the series aiding configuration. Let's now examine how current flows through step-up autotransformers. You'll note configured in this fashion, each winding is limited to a maximum of 1 amp. Consider a purely resistive 240 ohm load on the secondary. An application of Ohm's law, solving for current, demonstrates the load draws 1 amp of current from the secondary side of the autotransformer. An application of the AC power formula suggests the load consumes 240 volt amperes of apparent power, of which 240 watts is directed towards real power and 0 VARs is directed towards a reactive interchange. Assuming the autotransformer is 100% efficient, we could say power in equals power out, such that the primary input must also supply 240 volt amperes of apparent power. An algebraic manipulation of the power equation solved for current demonstrates the primary input side of the autotransformer draws 2 amps of current from the 120 volt source. An application of Kirchhoff's current law at the center tap demonstrates 2 amps of current enters and 1 amp travels through the load in a clockwise direction. This means 1 amp travels through the bottom winding top to bottom. What you achieve in a step-up configuration is 2 loops of current, both traveling clockwise. 1 amp of current circulates like this, and another amp of current circulates like this. The low voltage high current primary includes both paths, whereas the high voltage low current secondary side includes just one. Consider the amount of power capable of being transferred by the autotransformer. You recall, when configured as a traditional autotransformer, 120 volt ampere input resulted in 120 volt ampere output. You recall this transformer weighed 8 pounds. Configured as an autotransformer, the same 8-pound transformer uses both windings, each with a 120 volt and 1 amp rating, transfers a total of 240 volt amperes of power. As we observed in the step-down configuration, step-up autotransformers can transfer more power in a smaller, lighter, less expensive package. This being said, you'll note the single winding serving as both primary and secondary defeats the isolation feature of a traditional transformer because the primary and secondary are now electrically and physically tied together. As previously, I should note that a doubling of power rating is the maximum one might expect to achieve for autotransformers. Other turns ratios result in more power transfer, but not quite double as that of a traditional transformer with isolated primary and secondary windings. As an example, consider a traditional 1-to-3 step-up transformer with a 120 volt, 3 amp rated primary and a 360 volt and 1 amp rated secondary for a total power rating of 360 volt amperes. Let's say the primary is 1,000 turns and the secondary is 3,000 turns. Now consider these same windings configured as a step-up autotransformer in the following fashion, with 1,000 turns in the primary and 3,000 plus 1,000, or 4,000 turns in the secondary. The 1,000 and 4,000 turns ratios suggest this is a 1-to-4 step-up autotransformer. When 120 volts is applied to the primary, output would be stepped up to 480 volts. If we are asked to supply power to a purely resistive 480 ohm load, An application of Ohm's law solving for current demonstrates the load draws 1 amp of current. An application of the AC power formula demonstrates the load consumes 480 volt amperes of apparent power, of which 480 watts is directed towards real power and 0 VARs is directed towards the reactive interchange. Assuming the autotransformer is 100% efficient, we can say power in equals power out, such that the primary input side must also supply 480 volt amperes of apparent power. An algebraic manipulation of the power equation solving for current demonstrates the primary input side of the autotransformer must draw 4 amps of current from the 120 volt source. An application of Kirchhoff's current law at the middle tap demonstrates 4 amps of current enters and 1 amp of current travels through the load. This means 3 amps travels through the bottom winding. What you achieve in the step-up configuration is 2 loops of clockwise traveling current, where 1 amp travels like this and 3 amps travels like this, such that the low voltage, high current primary experiences both current paths, whereas the high voltage, low current secondary experiences one. Again, let us consider the amount of power capable of being transferred by the autotransformer. You recall, when configured as a traditional transformer, it was limited to a rating of 360 volt amperes. These same windings configured as a step-up autotransformer allows the device to transfer 480 volt amperes, an increase of 1.33 times, again without exceeding the rating of either winding. Alright, now that we've got a basic understanding of autotransformers in both step-down and step-up configurations, let's see if you can handle these beasts on your own. Given these circuits including autotransformers, see if you can first determine the autotransformer as a step-down or a step-up configuration, and then, once you've figured that out, determine the voltage, current, and power experienced by each load, as well as the current drawn from the source. Additionally, see if you can illustrate how current flows through the larger circuit. To keep things easy, let's assume these autotransformers are 100% efficient. The example on the left has an autotransformer with 2,300 windings in the primary and 2,000 windings in the secondary, being supplied by a 277 volt source with an 80 ohm at an angle 20 degree load. The second example on the right has 1,000 turns in the primary and 1,730 windings in the secondary. It's being powered by a 120 volt source, and the load is 57 ohms at an angle of 30 degrees. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Our first illustrated example features an autotransformer in a step-down configuration, and that the larger primary input side has 2,300 turns, whereas the smaller secondary output side has only 2,000 turns. This autotransformer has a 2,300 to 2,000 or 1.15 to 1 turns ratio. 277 volt primary input would be stepped down to roughly 240.9 volts. An application of Ohm's law demonstrates the load draws roughly 3 amps of current at an angle of negative 20 degrees. An application of the AC power formula demonstrates the load consumes 725.2 volt amperes of apparent power, of which 681.5 watts is directed towards real power and 248 VARs is directed towards a reactive interchange. Assuming the autotransformer is 100% efficient, we can say the primary input must supply the same amount of apparent power. An algebraic manipulation of the power equation, solving for current, demonstrates the primary input side of the autotransformer must draw roughly 2.6 amps of current at an angle of negative 20 degrees from the 277 volt source. An application of Kirchhoff's current law at the secondary tap demonstrates 2.6 amps of current at an angle of negative 20 degrees enters and roughly 3 amps of current at an angle of negative 20 degrees leaves. This means 392.7 milliamps of current at an angle of negative 20 degrees would circulate like this, and roughly 2.6 amps at an angle of negative 20 degrees would circle like this. What you get in the step-down configuration is 2 loops of current, both traveling clockwise. On the high voltage, low current primary side, it includes only one path for current, whereas the low voltage, high current secondary side includes both. The second illustrated example features an autotransformer in the step-up configuration, and that the smaller primary input side is 1,000 turns, whereas the larger secondary output side is 1,730 turns. This autotransformer has a 1 to 1.73 turns ratio. 120 volt primary input is stepped up to roughly 270.6 volts. An application of Ohm's law demonstrates the load draws roughly 3.6 amps at an angle of negative 30 degrees. An application of the AC power formula demonstrates the load consumes 756.1 volt amperes of apparent power, of which 654.8 watts is directed towards real power and 378.1 VARs is directed towards the reactive interchange. Assuming the autotransformer is 100% efficient, we can say an identical amount of apparent power is supplied by the primary. An algebraic manipulation of the power equation, solving for current, demonstrates the primary input side of the autotransformer must draw roughly 6.3 amps of current at an angle of negative 30 degrees from the 120 volt source. An application of Kirchhoff's current law at the tap demonstrates 6.3 amps of current at an angle of negative 30 degrees enters, and roughly 3.6 amps of current at an angle of negative 30 degrees travels through the load. This means 2.7 amps at an angle of negative 30 degrees travels like this, and 3.6 amps at an angle of negative 30 degrees travels like this. What you experience in a step-up configuration is two loops of current, both traveling clockwise. The low-voltage high-current primary includes both paths at 6.3 amps at an angle of negative 30 degrees, whereas the high-voltage low-current secondary side includes the 3.6 amps at an angle of negative 30 degrees drawn by the load. Alright, that's about it for today. As a closing observation regarding autotransformers, you'll note it would be possible to create a variable voltage source using an autotransformer with a sliding tap that changed the primary to secondary turns ratio such that, given constant input, output voltage could be varied as a function of tap position. On a very basic level, an adjustable autotransformer might form the primitive core of a fixed frequency, variable voltage magnitude power supply. Given a fixed number of turns in the primary, less turns in the secondary results in less output, and more turns in the secondary results in more output. In conclusion, this lecture introduced the autotransformer. We compared and contrasted autotransformers with traditional transformers and learned to perform circuit analysis on circuits including autotransformers. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.